Okay, hello. I begin. So some little reminder. So I recall we are dealing with Lie algebra. Lie algebra G L infinity, which is by definition the inductive limit of G L n's. And of course we can form the universal enveloping algebra. And as I showed, the center of this algebra is trivial. So our goal is to extend this algebra I will construct some extension, some large algebra, which will be denoted as capital A. The first step is to construct a future center. Future center of A is the algebra of shifted symmetric functions. The algebra shifted symmetric functions. I forgot to say that a detailed study of this algebra is contained in the paper by Andrei Kunkov and myself, which is published in Russian in Algebra and Analysis, which is translated as St. Petersburg Mathematical Journal, and it can be easily found in the archive. So I recall the definition of this algebra. It is a filtered algebra. Which is obtained in the category of filtered algebra as a projective limit. It's defined as a projective limit of the shifted symmetric polynomials. This is my notation for the shifted symmetric polynomials in n variables, and with respect to some natural projections. These projections is specialization of the last variable to 0, just as in the case of the conventional algebra of symmetric functions. And, let me skip the equivalent definition as a certain subalgebra of the algebra of formal power series or bounded degree in infinitely many variables. I also recall that our algebra is isomorphic as the algebra of polynomials of the ground field, that is C, but it can be any field. And some analogs of my notation was as follows. My notation, okay, so some shifted analogs of power sum symmetric function. C is a constant, a parameter which can be arbitrary. I'm sorry, excuse me. This is stupid. I'd like to write. This is an infinite collection of functions, shifted symmetric functions, and by definition, it's equal to the series of such a type. Infinity. Arbitrary fixed. Due to this correction, terms always well defined as a formal power series. Let me mention also the actually, as explained in our paper with Kunkov, there is no canonical choice for analogues of power symmetric functions, power sum symmetric functions, but there is quite a natural and canonical, in a certain sense, canonical analog of complete of analogues of complete symmetric functions and elementary symmetric functions. I don't use them, but let me give a definition. Simply, the definition is as follows. These elements to other systems of generators. The definition goes as follows. In terms, it's better to define them in terms of generating series. And again, in inverse powers. So by definition, the generating series looks as follows. And this series is well defined as a formal power series in inverse powers of a parameter u. So this is the definition of the generating series. And actually, to define the elements themselves, this is done because it turns out that we have this definition. And again, this makes sense because one can divide the numerator and the denominator by u. And then we can expand into a series of a form which we need. And likewise, exactly the same type of generating series for shifted elementary symmetric functions. And here we have the following definition, similar but a little bit different. And again, it makes sense. And let me remark that for ordinary symmetric functions, we have the equality like this. Such a type, and we have a similar equality, but with a little shift, which is as follows. This is already evident from the very definition that we have a relation and in our paper it's explained the origin of this definition, but this was a digression, and now I proceed to our main topic. So how to see that this algebra is a virtual center? In what sense? Of our universal enveloping algebra. How to understand it? By the very definition, what is an element of our algebra? It's a sequence. It's an infinite sequence where n is a shifted symmetric polynomials, and next the degree is bounded as n varies. And these elements are compatible with respect to the projection, which means that if you take this element and substitute, then we get and we want to understand. The idea is that we know that we have a natural identification with the center of and in a sense, this is already some justification of why we get something related to a future center. And actually one can prove, and this is easy to prove, actually not difficult, that I recall that we have a natural analog of irreducible polynomial representations. The symbol infinity, just to emphasize the fact that these are GL infinity modules. And lambda is a Young diagram or repartition. And one can show quite easily that any such module has the structure of inductive limit. Where this is my notation for irreducible polynomial GL module. And these modules are well defined for any fixed lambda. These objects are well defined, provided that the index n is large enough. And because, so the idea is that as a vector space, it is the union of this chain of vector spaces. And for n fixed, I'm sorry. So we have also identification. On the left, we have shifted symmetric polynomials, and on the right, we have central elements. of a universal enthalpy algebra of level n. And it turns out, it's not difficult to see, just to use the Gelfand-Zeitlin branching rule mentioned in the previous lecture, and using it, one can see that this condition, this compatibility condition, just means the compatibility condition for these elements. I mean that the restriction of this central element, which acts by a scalar, to the subspace, let me write it, the restriction of xn from to the subspace coincides with this is just because the value, what is this restriction? It's a scalar. And this scalar is but as lambda is fixed, we have that this n-tuple behaves as some finite sequence, the lengths of the rows of lambda, and next 0, 0, 0, 0, 0, up to infinity. And adding 0 does not change this value by the very definition of the projective limit in the definition of the algebra of shifted symmetric functions. So this explains in some way why we can treat the algebra of shifted symmetric functions as something related to the center of, at least it acts in a natural way for a natural family of irreducible modules. But this is only some preliminaries. Now I want to explain the main construction, which is called the centralizer construction. Maybe some questions about the algebra of shifted symmetric functions. So please ask. Okay. So I proceed to the definition of this construction, to the description of this construction. But I need some notation. So what I need the group GLN, general linear group of n by n matrices, and its subgroup, which I defined as follows. Here, by definition, M is subject to these inequalities. And the definition is as follows: n by n matrices. And next we have M as follows. So the matrices from this subgroup have this special form, which means that actually this group is isomorphic to GLN minus M. Just look at this corner, which is of a size n minus M cross n minus M. Okay. Next, I need its Lie algebra, the Lie algebra, GLN. I'm sorry, I switched from capital N to small n, and it's subalgebra. Which is also isomorphic to. And this is the Lie subalgebra of matrices. I'm sorry. The size is n by. Is this clear, the definition? So if something is unclear, please ask me. And now the main notation is as follows. To simplify the notation, I set A n is by definition the universal developing of G. And next the subalgebra, which is a centralizer, namely, it is the subalgebra of fixed elements, which is this one, with respect to the adjoint action of this subgroup. So again, we take the universal algebra, which is generated by arbitrary matrices of size n by n, and the group GLN acts by conjugations. And we consider the fixed subalgebra, the subalgebra of fixed elements, with respect to the action of this subgroup. The conjugation of a smaller subgroup. If we take, and this is the same, sorry, and this is the same. Why? Because our subgroup is connected. One can take the centralizer of the Lie subalgebra. That is the subalgebra of elements which commute with this subalgebra. And because this is the Lie algebra of this group and this group is connected, it's the same. So this is a centralizer, and hence the terminology centralizer construction. And now the idea is as follows. Okay, so we have the universal enveloping algebra, which is in my notation the inductive limit of these associative algebras. And it turns out that this object is too small for our purposes from the viewpoint of representation theory. It's a bad object, no center, for instance. So the idea is to enlarge it. And in a certain sense, it's small because we are dealing with inductive limit. And what about projective limit? Of course, well, it's impossible to define the projective limit. This is stupid. It does not exist. But it turns out that one can construct the projective limit of this algebra with m fixed and n getting large. And this is possible. So the idea is to take this limit. So let us fix m and let go n to infinity. And after that, take the inductive limit with respect to this index. So this is the idea. So what we want, our first goal, is to define a projection from such a projection. We want to define m, the lower index is fixed, and n is large enough, and we want to define this projection. And it turns out that this can be done just by imitating the construction of the Harish-Chandra homomorphism. This is why I spent some time to explain the Harish-Chandra homomorphism. Now we need a lemma, which is inspired by the definition of the Harish-Chandra homomorphism. And the lemma is as follows. So given n, let's define I plus n is the left ideal in our enveloping algebra generated by these matrix units. That is, we take the last column and our left ideal is generated by the matrix units which sit in this column. And likewise, we also need the right ideal in the same algebra. Generated by the matrix units in the last row. Okay. Now let's examine this subalgebra by the definition. What is it? We have to take the enveloping algebra and take this subalgebra, but this is simply one-dimensional, trivial one-dimensional algebra, so this is precisely the centralizer of this element. Now After these preliminaries, the claims of Lambda are the following. First, for any element of our centralizer, there exists a unique element here, which is generated by the matrix units inside this block, such that A belong that is the difference between modulo. So in other words, modulo this left ideal, any such element which is in this centralizer can be reduced to this block. And the second claim is that we also have this. The next claim is that, and because the claim says us that B is unique, and we get a correspondence from A to B, and this is an algebra morphism. From our centralizer to the smaller universal enveloping algebra. And fourth, the last claim is that under the same projection, this subalgebra is sent to of course, provided if we have this restriction, because to define this object, we need this restriction. So this is exactly, at least the beginning, this is exactly an analog of the Harish-Chandra homomorphism. Why? So look at A, and we can expand, we can write it as a linear combination of monomials, ordered monomials, and the order. So let me write. We write the linear combination of ordered monomials following the assumption that such that on the left we take these matrix units, then in the middle we have the block. We can put anywhere the last entry, for instance, here. And we see that if we have a monomial, and using some natural order on this part and on this part in order to get uniqueness. And then we remark that provided our element A commutes is contained in the centralizer, that it commutes with this last matrix units. We have that once we have something on the right, we have also something on the left, and the same trick. This is the same trick. So this explains the equivalence between this and this. And our projection is obtained as follows. We just remove all monomials which contains these elements on the left, on the right, which amounts to the same. And what remains is B. And again, by the same trick, which shows that the kernel of our projection is actually a two-sided ideal, namely the intersection of our centralizer with the left ideal is the same as its intersection with the right ideal, so it's a two-sided ideal, so this map is an algebra morphism. And the last claim is also quite evident, especially evident if we apply the definition in the form that this subalgebra is the subalgebra of fixed elements with respect to the group, and not the algebra. And because this is some subalgebra here in this block, it commutes with the projection. And so if our elements A was contained in this subalgebra, it is also contained in this one. So the proof is easy and essentially repeats the construction of the Harish-Chandra homomorphism. So maybe ask if something is unclear. Okay, no questions. Okay. So this is analog reconstruction. This projection imitates the Harish-Chandra homomorphism. Now what next? Now we can define our algebra. First, that m is a non-negative integer, and we define this algebra as a projective limit as n goes to infinity of the centralizers in the category of filtered algebras. Just as in the definition of symmetric functions and shifted symmetric functions, this is very important. And this exactly means that the element A our algebra is a sequence such that it's contained in this centralizer, and there is a natural compatibility condition. And finally, because we insist on the fact that this should be a filtered algebra, the degree is bounded as n goes to infinity, remains bounded. And then we get an algebra. So we get a filtered associative algebra. And all operations are, by the very definition, are component-wise. So if you want to multiply, then we multiply the coordinates, and the same for addition and multiplication by scalars. So associative algebra and natural filtration because of this restriction. And I notice that what is this? And this is by the very definition, this is the center of AN, which is the center of GL. And our projection, and this is nothing else than isomorphic and shifted symmetric polynomials. And our definition is exactly, our projection is the same under this identification. Under this identification, our projection becomes the specialization of the last variable to 0. So we conclude that this algebra is the same as the algebra of shifted symmetric functions. The next step is that we have natural embeddings. This is because we have natural embeddings. Why? Because this is the centralizer of GLM, this subalgebra. And this is the centralizer but this subgroup is smaller than this one. By very definition, we are equal the definition. This is the block of size M. If M grows, our subgroup becomes smaller. And because the subgroup becomes smaller, the corresponding centralizer becomes larger. So we have this embedding. And this embedding is quite obviously commuting with our projections as n goes to infinity. And from this, we can conclude that we have these embeddings of a projective limit. And finally, final step of our definition. This is follows. Our algebra A is defined as the inductive limit of this algebra, which is simply a union, because this is the union of an ascending chain of subalgebras. And the embeddings are compatible with the filtration, so we see that this is again filtered algebra. Filtered algebra. The next observation is that we have a natural embedding. How to understand this? It suffices simply to remark that this object, it is precisely the subalgebra of stabilizing sequences, which means that for n large enough, because in one direction, how to get this embedding. So take some element, say x, this algebra, and it is contained in some, by the very definition, because this algebra is the inductive limit of this algebra, so our x is contained here. But then it turns out that x is contained in the centralizer as n is equal or bigger than m, by very definition, because our x lies here in this block, actually. This is 0. And so it commutes with everything which sits here. This means that it is inside this. Okay? Is it clear? Not? And by the very definition of our projection, as if we take, we take an equal, identically equal to x. And this definition also implies that the compatibility with our projections, which is absolutely trivial. And consequently, this implies that this stable sequence, which starts from some n, from m plus 1, it is not defined above this moment. It's not important. So we have x X, X, and so on. It's correctly, it's a well-defined element of our algebra. So this argument shows that we actually have this embedding, and the little argument also shows that okay, so this is the proof. This is the proof. So we obtained an extension of our algebra. This is the desired extension.
А вот это, вот, ну мы как-то взяли, решили бесконечности, пополнили или что-то такое сделали. Можно это как-то более явно, что ли, сказать? Что мы какие-то бесконечные суммы разрешили с какими-то условиями? Нет?
Знаете, тут ведь какая картинка? Эта конструкция очень похожа на конструкцию симметрических функций. Там, да, там действительно можно писать какой-то... Да, ну, пожалуй, я это... Тут ситуация похуже. Тут ситуация похуже. Я бы сказал так. Это фильтрованная алгебра. У нее есть присоединенная градуированная алгебра. Она уже будет коммутативна, но она на самом деле будет алгеброй Пуассона. Ну, не так важно. Она уже будет коммутативна. Так же, как... Это как бы аналог симметрической алгебры. И вот ее элементы действительно можно формально написать как некие бесконечные суммы. Но здесь ситуация посложнее, и это будет через некоторый момент будет видно. Поэтому представлять эти элементы как ряды, а вы знаете, нет, да, пожалуй, одну вещь я могу сказать. Да, я не сразу сообразил, да, можно. Для этого нужно вот что сделать. Я забыл про это совершенно. Let me say in English. So the question is about the possibility to represent the elements of our algebra A as some infinite series. And it's possible, but to do that, it's convenient to use differential operators. Actually, as any universal unvaluable algebra of some Lie group can be realized as the algebra of left invariant differential operators on the group. Here, the relevant group is GLN. But in this case, the left invariant differential operators can be actually viewed as differential operators on the space of all matrices. This is because the coefficients are polynomial. And so the differential operators can be extended from GL, from non-singular matrices to arbitrary matrices. They are well defined. And then it turns out that our algebra A can be realized in a natural way as a certain algebra of differential operators on infinite size matrices. And these differential operators can be viewed as some infinite series. So this is a possible answer to your question.
Thank you.
Okay, so let me continue. So what I would like to say, we have the following result, quite easy, proposition. Is as follows. A0 is exactly the center of our algebra A. How to prove this? In one direction, it's clear. What is clear? That A0 is contained is contained in the center. Why it's so? But again, look at the fact that any A is an infinite sequence, and the operations are component-wise. So this is an element of because the operations are component-wise, and because for this subalgebra, all the components are central, we get this inclusion. And to get the opposite inclusion in the opposite direction, we observe that any x from omega in A from the center must commute with G of infinity, which is embedded into our algebra. So this means that the components must commute with x from G infinity. But this means that as n is large enough, taking any element it should commute with all GLN. What I would like to say is this. This component must commute with all this subalgebra, so it must be central. So all coordinates must be central, and this exactly means that we have the opposite embedding. So this is the center. The center of our algebra is the algebra of shifted symmetric functions. And finally, not finally, but the main result of this construction, main result of the construction. I'm sorry, I would like to postpone this. And first of all, I would like to say that, of course, A0 is contained and it's central, but it's not true that it exhausts the whole center of this object. It's not true. The center is larger than this one. And why we will see in very quickly. The main result of the construction is as follows. So the theorem which explains the structure of our object, the algebra. So assume is isomorphic to the tensor product with the Yangian. The Yangian of G. And if we denote, so we also have embeddings. Which enables us to define the infinite size Yangian is the inductive limit of the Yangians. And the structure of this big algebra A, it is isomorphic to this object, which is algebra of shifted symmetric functions times this Yangian. And from this fact, it follows why this is not the whole center, because we have a quantum determinant. And the quantum determinant is a central element. More precisely, it is a generating series for certain central element here, which generate the whole center of a Yangian. So the whole center of this algebra is generated by the algebra of shifted symmetric functions and the components of the quantum determinants. But for this algebra, it's impossible to define the quantum determinant, just as because it's of infinite size. So this is the main result of this construction. And it gives us an alternative approach to the Yangian. We can start with this construction, this projective limit construction, and then examine what we get. And after that, we found that we get something which can be identified with the Yangian. Of course, we need to use the RTT relation and so on. But this explains, and let's see a little bit later, this it explains how this Yangian, this Yangian arises. So look again. At the beginning, we have this algebra. And the point is that this algebra, one can extract from it something larger, this algebra A. This is inductive limit. And modifying in a certain way this construction, that is replacing the inductive limit by some tricky projective limit, we get this object. So this is some phenomenon of infinity. Let me say in Russian maybe. Мне хочется сказать, что вот эта вот алгебра, она с одной стороны, ее структура бедная, но она из самой себя извлекает гораздо более богатый и содержательный объект. Вот эту алгебру. И такой феномен бесконечности, как бы бесконечно-мерного объекта. Он потенциально содержит в себе нечто большее, чем представляется на первый взгляд. Это, как бы, мне кажется, такой вот главный такой итог вот этой конструкции. Нечто новое по сравнению с тем, что мы знаем, оставаясь в рамках конечномерных обычных алгебр, обертующих алгебр. Нечто совершенно новое. Принципиально новое то, что приходит к нам из рассмотрения бесконечномерных групп и их алгебр Ли. На самом деле это связано с представлением. Вот. Ну, теперь, что what next? The next topic I would like to discuss is as follows. The algebra A acts in a natural way in a natural way in these representations. So these are representations of the ordinary algebra and ordinary universal envelope algebra, but there is quite a natural way to extend this action to this larger algebra. So this shows that our construction, this is some justification in a certain sense of our construction. It shows that our constructions is rather natural from the viewpoint of representation theory. So we get some extension, some completion in a certain sense, and this completion is compatible with representation, at least with certain representation. The simplest representation, which are these polynomial representations. And how to see this? Okay, so let me explain this result. I need one more notation. One more ideal. Left ideal in U J infinity. By the very definition, it is generated by the matrix units. So our algebra, this algebra, is generated by arbitrary matrix units. And this ideal is generated by the matrix units such that and let me draw a picture to explain this. I have this picture. So what is, this is the block n by n, and the matrix units, this one, are contained here. There are on the diagonal and on the right. Okay. This one. And now the definition is as follows. So what we have. So J sub 0 is just the generated by n plus. I mean the strictly upper triangular matrices. And then we have a smaller ideals because we have a smaller family of generators. And smaller and smaller, this is a descending chain of left ideals. And given a GL infinity 2, let us set, I need some notation. Sorry, maybe it's not very good, but annihilator of its left ideal. It's enough to say that this is annihilator of the matrix units which generate this ideal. It's the same. And because the ideals form a descending family, we get an ascending family of subspaces. So we have and let's say by definition the union of these subspaces. And the observation is that is a submodel Why? The reason is very simple. It's very simple because we have one reason is that explanation is that is stable under conjugation by means of G.L.n, which is contained in GL infinity. Or another explanation is as follows. This is a left ideal, but if X belongs to GLn, it follows that with left ideals, this is contained. One can say that, in other words, GLn is contained in the normalizer of this left ideal. And from this one can deduce that we get a submodel. And for instance, this means that if our V is irreducible and this subspace is non-zero, in principle, it may happen that our object is simply a zero. But if it's non-zero and our model is irreducible, then it must coincide with the whole model. So one can introduce a category definition, category omega of GL models as follows. V is omega if for instance, take the tensor models, the tensor G infinity models are omega. What I mean by this claim, I need some notation, say script V is the inductive limit here. Maybe I should use small n here. So these are infinite vectors with finitely many non-zero coordinates. This is an analog of the column vectors of length n. But here we take column vectors of infinite length, but with finitely many non-zero components only, a quantumly dimensional vector space. And again, we can take tensor products, and I recall that the decomposition is governed by the Schur-Weyl duality. So these are precisely the irreducible components. Components are precisely the polynomial modules, and they all are in our category. Why? It's very simple. Because what is the action? What is the action? The action of on a weight space. On a weight space mu. In our situation, in tensor module, any such mu contains only finitely many non-zeros. So any weight is of the form 0, 0, 0, 0, and so on. And the action of such an element, what it produces. It means for I with 1, it means that we add leads to adding and if J is large enough, so if it's contained in this and N is large enough, then this action annihilates this element, annihilates our any weight vector. Why? First of all, if this element is diagonal, that is I is equal to J, it's trivial because we just get the multiplication by these coordinates, which is 0. And if it's not diagonal, then we have to subtract 1 from 0, and we get something with strictly negative components, strictly negative coordinates. But such coordinates do not exist in our situation because we have polynomial modules. So we get 0. So this explains why our tensor representations are contained in this category omega. And finally, we have this very following proposition. Suppose V is contained in this category, means that the action of our algebra is extended to this larger algebra A. Why? The idea is as follows. We want to extend, we take some element which is in A. It follows that as n large enough, then an is contained in sum for some m and all. Maybe I have to remove this. And then it follows that for any v in vector, the element stabilizes as n goes to infinity. Why? This is because v is contained as n is large enough. And then, which means, that v is annihilated by this ideal. But we have that the difference by the very definition of our algebra is actually contained in this left ideal. So as n gets large, the difference between the coordinates does not matter for this object. So we have stabilization. And then one can prove that we actually get not only some definition of what is this object, but it actually is an action of our algebra. Well, so I have to explain the isomorphism. I have to explain this result, but this will be the topic of the next lecture. I will explain why this happens. Okay, let's stop at this moment. I will switch off the record.